Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of basic electrical and electronics engineering. We'll dive into key concepts like equivalent circuits, phasor diagram, voltage regulation. Slide 1. Equivalent circuit of a single-phase transformer. Let's begin with the concept of the equivalent circuit of a transformer. We know that an actual transformer is not ideal. It has losses and imperfections. So, to analyze its performance more practically, we use an equivalent circuit. This circuit represents all the real electrical characteristics of the transformer using simple elements like resistors and inductors. 1. The primary resistance, R, represents the copper loss or I squared R loss in the primary winding. 2. The primary leakage reactance, X, models the magnetic flux that doesn't link to the secondary. This is called leakage flux. 3. Similarly, on the secondary side, we have R and X, which represent the same losses and effects in the secondary winding. 4. Then, to represent what's happening in the core, we introduce two more components. Core loss resistance, R, this accounts for eddy current and hysteresis losses. These are losses that happen inside the core due to alternating flux. Magnetizing reactance, X, this accounts for the magnetizing current needed to create flux in the core. Now, since having two sides, primary and secondary, in one circuit is complicated, we often convert all elements to one side using the turns ratio, A equals N. This gives us the referred equivalent circuit, either referred to the primary or to the secondary side. Example, suppose a transformer's secondary resistance is 0.2 ohm, and turns ratio is 2:1. Then, referred to primary, the resistance becomes 0.2 times 2 squared equals 0.8 ohm. Significance: this model helps in analyzing transformer performance, voltage drop, efficiency, and regulation can be easily calculated. Slide 2. Phasor diagram of transformer on load. Now let's discuss the phasor diagram, which is essential in understanding how voltages and currents behave in AC systems. A phasor is a rotating vector representing sinusoidal waveforms. In transformers, we use phasor diagrams to understand how voltages and currents are related in terms of magnitude and phase angle. The phasor diagram changes based on the type of load connected, inductive, capacitive, or resistive. 1. The core flux, phi, is taken as the reference. The induced EMFs, A and A, are in phase with this flux but in opposite directions. 2. When no load is connected, the transformer draws a small current I, which consists of I, the magnetizing component, lagging phi by 90 degrees. I, the working component, in phase with voltage and responsible for core losses. 3. On load, current increases and the total current becomes I, and due to impedance R and X, the applied voltage V is ahead of A. 4. The angle between voltage and current shows power factor, lagging for inductive loads, leading for capacitive loads. Example, if current lags voltage by 30 degrees, it indicates an inductive load and power factor is cos 30 degrees, approximately equals 0.866. Significance: helps engineers predict the performance and design of transformers under various load conditions. Slide 3. Voltage regulation of transformer. Now let's understand what voltage regulation is. Voltage regulation measures how much the voltage drops when a transformer is loaded compared to no load. Ideally, we want the voltage to stay constant, but due to internal resistance and leakage, it drops when current increases. Here, we know load as the voltage at secondary when no load is connected. We full load as the voltage when the transformer is supplying full rated load. 1. Positive voltage regulation, common with inductive loads like motors, voltage drops under load. 2. Negative regulation occurs with capacitive loads, where voltage may rise slightly under load. 3. Voltage regulation also depends on the power factor of the load. 4. A good transformer has voltage regulation under 5% for most applications. 5. Helps choose the right transformer for sensitive equipment. Example problem. If a transformer gives 230 volts at no load, and voltage drops to 220 volts at full load. VR equals 230 to 220, 220 times 100 equals 4.54%. Significance. Lower voltage regulation means better performance and stable voltage supply. Slide 4. Explanation of key parameters. Let's take a quick overview of the parameters we use frequently in transformer analysis. R represent copper losses, I squared R in primary and secondary winding respectively. X represent leakage reactance due to imperfect magnetic coupling. R represents core losses, due to hysteresis and eddy currents. X represents the magnetizing current needed to establish flux. A induced EMFs in primary and secondary, proportional to d phi dt. V terminal voltages applied and obtained across windings. Turns ratio, A equals N, ratio of number of turns in primary to secondary, decides voltage conversion. Voltage regulation percentage drop in voltage when the transformer is loaded. Tip: these parameters are used for designing, analyzing, and troubleshooting transformers.